Welcome to Let's Get to the Marks. We're looking at GCSE Chemistry Paper 1 from 2023. And you've got about an hour and 45 minutes to do this. It's worth 100 marks. So let's get into it. Don't forget to pause the video and have a go between the questions before unpausing and watching the answers. Discoveries in chemistry led to a better understanding of atomic structure. Atoms were originally thought to be tiny spheres that could be not divided or not be divided. The plum pudding model of the atom was then developed. This represents the plum pudding model of the atom. Describe the plum pudding model. Right, key word here, you have to use the word sphere or ball. Basically, you can't say circle. You need to give the examiner the impression you understand it's a three-dimensional structure. So use the word ball or sphere. It's a ball or sphere of positive charge, 1 mark. Embedded with electrons. You can say electrons are stuck throughout it. You can see those minuses in the circles. They're supposed to be the electrons or the plums within the pudding. Think of chocolate chips in a cookie, or better yet, blueberries in a blueberry muffin, where the muffin is the positive charge and the blueberries are the electrons embedded within. Okay, 1.2. Atoms contain electrons, neutrons, and protons. Write these 3 particles in the order of discovery. Well, you can see from the plum pudding they'd already discovered the electrons, the little circles that are negative. They then discovered protons after the plum pudding model, once they made the nuclear model, and after that. And the last thing was James Chadwick, who discovered the neutrons well after the model of the atom had been developed. Obviously, neutrons have no charge. It was a lot harder to trace the existence of neutrons. Very few atoms of the element TS have ever been identified. The atomic number is 117. Predict the number of electrons in the outer shell of tennessine. Give 1 reason for your answer. Use the periodic table. So if we look at the periodic table, we will find what group of the periodic table tennessine is in. And if you look up what group tennessine's in, so if you go to your periodic table and have a little look, you're going to find that tennessine is in group 7. So it's a halogen, just like fluorine, chlorine, bromine, and iodine. Then you have to ask yourself, if you're an element in group 7, how many electrons will be in your outer shell? And of course, the answer is 7. So the number of outer shell electrons we could reasonably predict for tennessine would be 7. And the reason is because it is in group 7. And that's how many electrons are in the outer shell. Right, the next question. Tennessine was first identified by a small group of scientists in 2010. Suggests 1 reason why tennessine was not accepted as a new element by other scientists until 2015. So why did it take so many years to accept tennessine? 5 years before people said it's an element. Well, the other scientists needed to test the element. It required more evidence for its existence. In science, we don't just rely on someone saying, oh, look, I've discovered this. We needed peer review, other scientists to review their work and copy the work and see if they get the same results. Okay, 1.5. The discovery of isotopes explain why some relative atomic masses are not whole numbers. Element R has 2 isotopes. Table 1 shows the mass number and percentage abundance of the isotopes of element R. So we've got mass number 6, mass number 7, we've got their percentage abundances. Calculate the AR of element R and give your answer to 1 dp, 1 decimal place. Really key to highlight keywords when you're going through an exam paper. Using a highlighter or circling or underlining words helps you focus, helps you not lose any of the information. Okay. How do you work out the AR? You do the sum of the abundance times the mass of each element. Okay, so you're going to individually times the mass number by the percentage abundance for each element, add them together. So 6 times 7.6 and 7 times 92.4. Add them together and then divide by the total abundance, which is normally 100. Then you're just going to smash that in the calculator, and you will get your AR. Now, if you're thinking about it, doing a mental correction, should the AR, the mass, the combined mass of this element R, be closer to 6 or 7? Well, let's have a look. 92.4 of the elements have the mass 7 and 7.6 have a mass 6. So obviously there's way more with a mass of 7. So we're expecting our answer to come out close to 7. And this is the way you can mentally check if you've done it right. The answer should be close to the number 7, because it's like having 100 people in a room and 92 of them weigh 7 and only 8 of them weigh 6. You would expect the average weight to come closer to 7. And that's what we're looking at here. So the answer is 6.92. Don't forget, we've got to round this to one decimal place. So we're going to make that 6.9. If it was 6.95 or 6.96, we'd round it up, okay, to 6. Okay, whoops, what am I doing? We've rounded it up to 7.0. Right, question 2. The question is about temperature changes. A student investigated the change in the temperature of a solution when different masses of ammonium nitrate were dissolved in water. This is the method used. So we've got our lovely method here. Give the independent variable and the dependent variable in the investigation. Don't forget, the independent variable, can't even speak there, the independent variable is the one that you change. Okay, so it's the thing that you're testing, you're changing in your experiment. The dependent variable depends on the experiment, not on you. You're not in control of it. It's what you measure. Okay, so i.e. the amount of carbon dioxide given off, the amount of oxygen bubbles released. Those things are what you can measure. So what are we changing? Well, you can see here it says add 4 grams of ammonium nitrate, and then we're doing it with different masses. Different being the key word. We are changing the mass of ammonium nitrate. Now, what are we measuring? Well, let's have a little check. We might be able to read this. It says there, measure the lowest temperature reached by the solution. So our dependent variable comes with the word measure. So we are measuring the temperature of the solution. Okay, and that will get you your 2 marks. Let's move on. Oh my days, it's a graph. Right, I'm going to have to split the screen here so we can see the table of results and the graph. It says plot the data from table 2 on figure 2. They seem to have labeled the axes for us, so this is only going to be like 3 marks. Like normally if you have to label the axes, 3 marks for just whacking the titles in. So let me just split this up and get this ready. Okay, the first thing to work out is how many squares are in between. We're going to do the bottom axis here, which is our independent variable, the mass in grams. And there are 10 squares, but only 5 units on the measurement scale. So we need to do 5 divided by the number of squares. So 5 divided by 10. Each of these little squares on the bottom are worth 0.5. So each one of these is worth 0.5. And then I need to do the same sort of scale on the other side, okay, on the y-axis. And what we're going to find here, it's only 2 in the measurement scale, but again, there's 10 squares. So we're going to do 2 divided by 10. Each baby square going up the y-axis, going up vertically, is only worth 0.2. So when we go horizontal, each square is 0.5. When we go vertical, each square is 0.2. And that's an important thing to work out when you're going to do graph plotting. So the first point is we're going to 4 across, and we're going to zing up to 18.2. And then we're going to go to 8 across. So remember, each square is worth 0.5. So I need to add 6 of these bad boys, as that all equal 3 to get my 8. And then I go up here and I've got 16.2. Okay, now I want to do 12 and 15.2. So again, I'm going to need to count 4 baby squares. Each one's worth 0.5. And then go up here and we're going to go 15.2. So just above one little baby square above 15, as vertically each square is 0.2. And then I'm on to 16 and 13.6. So for 16, I just need to go 2 squares across, because each one's 0.5 on the bottom. And then vertically, I need to go to 13.6. And then again, horizontally for our final plot, we're going, oh no, we've got 2 more to do. So this one's 20, and I'm going to 12.4, and the last one is 24. So 2 baby squares before the 25, and then going up to 10.6. each little square is worth 0.2, so I go 3 squares up. And there you go. Now you've got to put a line of best fit through. So try to go through as many points as possible with a straight line. Now, you don't have to track it all the way back to the axes here, like I'm doing here. You don't have to do that, but that will probably be asked later on in the question if we need to extrapolate results. Okay, so after 3 marks for plotting the graph, we're looking at show what the initial temperature was. So yeah, really you just got to follow your line of best fit back. I need to draw my line of best fit a little bit more accurately than this. I mean, it's going through quite a lot of the points there, but I probably should only do the first one because then they ask us to extrapolate it back. And what they mean by extrapolate, follow your line of best fit back so you can make a prediction about something you didn't record. So look here, we only actually started recording there, but if I follow the line back, I can get the data when no ammonium nitrate was added, so I can get the initial temperature would have been there. That is the temperature when no nitrate was added, so that's about 19, maybe 19.8, pretty close to 20 to be honest, but it's about 19.8. Now, how do the results show that dissolving ammonium nitrate in water is endothermic? That's the next question. How do the results show that dissolving is endothermic? What's happening to the temperature as we add more ammonium nitrate? Well, look, the lowest temperature recorded is going down. So what we can see here is that means, going to a full-size graph, that means that the temperature is decreasing. So what that's telling us is more energy is being absorbed than is being released. So the evidence that this is an endothermic reaction, temperature goes down as we add more ammonium nitrate. Coolio. Let's move on. We're nearly, where are we? Nearly the end of the question. The student repeated the experiment 3 more times. Here's the results for 8 grams of ammonium nitrate. Trial 1, trial 2, trial 3, trial 4, and we have a mean of 16.5. The student recorded the mean lowest temperature of the solution for 8 grams of ammonium nitrate, 16.5 plus or minus 0.3. Explain why the student included the plus or minus 0.3 after the mean lowest temperature. Well, let's have a look. The mean was 16.5. What's the lowest around the mean? Was 16.2. What's the highest set of data? The highest set of data was 16.8. So look, 16.5 minus 3 is 16.2. 16.5 plus 3 is 16.8. So this shows the range around the mean. It gives you an idea of how accurate your repeats were as well. The smaller that range is, the more reliable your data is because you've carried it out really accurately. You've got your results clustered close together. So the highest temperature was 16.8, which is plus 0.3. And the lowest temperature recorded was 16.2, which is minus 0.3 around the mean. This shows the range around the mean. And here we go. Boom. So, what type of error is shown by the results in table 3? Random error, systematic error, or zero error? Well, what do they mean? Well, look at these results. They're not all the same. Why didn't they all come out as 16.5? Or why didn't they all come out as 16.6? Why have we got a little bit of variation in the results? Well, we'll call that random error. Systematic error means you've made a fundamental mistake with your method, using a measuring cylinder instead of a gas syringe or something like that. You've made a mistake. A zero error is when you haven't calibrated your equipment properly. So if you're measuring the mass and you didn't make sure the scale was on 0, that would be zero error. So all your masses will come out wrong because you've not zeroed the equipment. Random error is the most difficult error to account for because this is the error by slight changes in the temperature or the environment that you cannot control. It's beyond the experimenter, the person carrying out the investigation's control. You can't really control random error. It's slight variations in the equipment, slight variations in the environment that you can't control. Whereas systematic error is when you consistently are making the same mistake every time, i.e. using the wrong equipment or measuring in the wrong way. All right, guys, let's move on to the next question. Okay, question 3. This question is about making a soluble salt 3.1. Plan a method to make pure dry crystals of zinc chloride from zinc carbonate and a dilute acid. So you should know this off by heart. That's the most common salt question for AQA. Now, we're going to write an equation from this. Basically, we know we've got acid plus zinc chloride. No, acid plus zinc carbonate is going to make zinc chloride, which is the salt, plus water and carbon dioxide. Now, they've told us that one of the reactants is zinc carbonate. We make the zinc chloride from zinc carbonate. And then the other reactant is dilute acid. You're obviously going to get one of the 6 marks here from naming the acid. So you should be able to work out that it must be hydrochloric acid. Hydrochloric acid make chloride salts. Okay, what do we do with that acid? Well, we warm the acid in a beaker and then you're going to add the zinc carbonate. Okay, and you're going to add it till it's in excess. So over here on the diagram, you can see we've got zinc carbonate crystals going in. What happens by adding till excess? It means add it until the zinc carbonate doesn't disappear anymore. Now, zinc carbonate is going to bubble away because of carbon dioxide as it reacts with the acid. Eventually, you're going to add some zinc carbonate and there's no acid left. The zinc carbonate's then in excess. So what you want to do then is filter off the zinc carbonate using filter paper and a funnel, which you could also add into your answer, and then gently evaporate some of the water until you see crystals appear. Some people say use a glass rod to help crystallization happen. So once you see crystals appear and they start to form, those are the salt crystals. You take the evaporating basin or the beaker off the heat and you leave to cool and crystallize. We call this process crystallization. Just get the word crystallization or crystallize in and you'll pick up the mark. And that's for the leaving to evaporate by itself, okay, without a heat source is crystallization. Now, some people will say refilter. You don't have to, but you could say refilter and then dry with a paper towel. And drying with a paper towel, the clue's in the name. It asked you for dry crystals. So whenever you see that, you know you're going to need to say dry with a paper towel. And that's your 6 marks. All right, let's move on to 2.2. Name 2 other substances that can each be reacted with a dilute acid to make zinc chloride. So we had zinc carbonate. We'll just pick anything else with zinc. So zinc oxide is another alkali that will neutralize an acid. And you could just use zinc metal. That will make zinc chloride too, although not a neutralization reaction. Right, moving on, figure 3 shows the displayed formula for the reaction between hydrogen and chlorine. We've got the bond energies here, 436 for hydrogen, 346 for chlorine, and 432 for hydrogen chloride. Which expression shows how to calculate the overall energy change for the reaction? Now, remember, the energy change is going to be the reactants, the left-hand side of the arrow, minus the right-hand side equals the energy change. I've used the enthalpy symbol here, which you don't need to know at GCSE. So what's the left hand minus the right hand? If you go up above and add up all the bonds in that table, you'll find that the answer is D. Now, let's move on. 4.2, the reaction between hydrogen and chlorine is exothermic. What is an exothermic reaction? Explain why this reaction releases energy to the surroundings. Why do exothermic reactions give out heat or give out energy? So if you just say they give out heat, you're not going to get the mark. What we need to say is, why does it give out heat or why does it give out energy? And going back to the previous question, if you add up the energy absorbed in breaking bonds in the reactants, as this was the correct answer for 4.1 was D, this is the energy in bond breaking was 782. If you do 2 lots of 436 plus 346, sorry. And then if you do 2 times 432, you get 864. That's the energy that's been released. What can you say about the energy that's been absorbed in bond breaking and the energy released in bond making? What can we say about them? We can see there's a difference. And you get an exothermic reaction when the energy that goes in to break bonds is less than the energy released in bond making. And that's the answer for 2 marks. Energy absorbed in bond breaking is less than the energy released in bond making. Okay, 4.3 shows part of a reaction profile for the reaction between hydrogen and chlorine. Label the activation energy and the overall energy change. So this is 3 marks. You're going to get 1 mark for drawing your products lower than the reactants. So in exothermic reactions, the products end up lower than the reactants, and that's because we've had some energy released in the environment, they're more energetically stable. Now, I'm using the symbols AE, but you can use EA for activation energy, energy of activation, or activation energy. Use a dotted line here, and I've drawn an arrow going down because the energy is released. That's my enthalpy symbol or energy change symbol. You can just write energy change. You don't need to use symbols. You can just write activation energy. And the activation energy is the size of the kind of camel's hump. Draw a dot and cross diagram for a molecule of hydrogen chloride, HCl. Show the outer shell electrons only. First of all, we need to ask ourselves, the first question when doing bond drawings is it ionic or covalent? And as it's made of non-metals, it's covalent. So we draw the Venn diagram, the kind of two circles overlapping. So hydrogen only has one electron, it's in group 1. Chlorine's in group 7, has 7. So pluck those on first. Plot, pluck, whatever. And you can do it like this, where you draw them on the line, or you can draw them inside the gap formed between the two circles. Up to you. And that's worth 2 marks. Okay, 4.5, figure 1 represents molecules of methane and of polyethylene. Methane is a gas at room temperature and polyethylene is solid. Explain why methane's a gas and polyethylene is a solid at room temp. Now this is down to intermolecular forces. First of all, methane and polyethylene are both made of non-metals. They're both covalent molecules, and they're both simple molecules. Methane is a small, simple molecule. And what do we know about simple molecules? They have weak intermolecular forces, which are easily broken and do not need a lot of energy to break. Now, polymers are actually large molecules, but they're still simple in their structure. So they are large, simple molecules. They have stronger intermolecular forces and therefore require more energy to break those forces. And that's why they're solid. So anything that's a gas or liquid at room temperature is normally a simple molecule with weak intermolecular forces, not a lot of energy needed to break. And that's a good thing to remember. Question 5, this question is about acids and alkalis. Ethanoic acid is a weak acid. What's meant by the term weak acid? Answer, using the word ionization. So weak acids partially ionize in solution. If they hadn't use ionization, you could say dissociate. But here they've specifically asked for you to use the word ionization. Now, you don't need to write this equation, but you should know this off by heart if you're doing triple. This is the equation for ethanoic acid, which is a weak acid, and the reversible symbol shows that it is only partially breaking down, okay, into ethanoate ions and hydrogen ions. Right, let's zing to 5.2. The concentration of acid can be measured in mole per dm. Which combination of changes increases the concentration of acid? So how do you increase the concentration? Mass of the acid dissolved is halved and the volume of the solution is halved. Well, if you're going to half the mass and half the volume, the solution will stay the same because you'll have the same amount of particles in the same space. The only one that's going to decrease is the second one, because what you're doing there is you are halving the mass and making the volume bigger. So you've definitely got less particles in the same space. Right, 5.3, the concentration of an acid can be determined by titration. Basically, name the indicator and the color change. So one of the indicators you need to know off by heart is methyl orange. It's yellow in alkali and red in acid. As the alkali is first into the tube, we're talking alkali first. Now, the other one you can use as an alternative is phenolphthalein. Phenolphthalein is pink in the flask with the alkali and colorless when it turns to an acid. So pink and colorless for phenolphthalein. Right, 5.4, sodium carbonate dissolves in water to produce an alkaline solution. Give the formula of the ion that makes a solution alkaline, and that's the OH minus, the hydroxide ion. Just for your notes, remember that the hydrogen ion H plus is what makes something acidic. They often ask that too. A student does a titration using sodium carbonate solution in nitric acid. Here's the equation, and we've got to pay attention to the coefficients. We've got 25 centimeter of 0.124 mole per decimeter sodium carbonate, and it's neutralized by 23.6 centimeters of nitric acid. Calculate the concentration of nitric acid and give your answer to 3 sig figures. So we're going to need the moles over concentration times volume, which is your titrations equation. You need to know that off by heart. So the first things first, you should all be able to work out that we've been given the volume and the concentration of sodium carbonate. So go ahead and work out the moles. And so we do 25 over 1,000 because we've got to convert to decimeters times the concentration of 0.124. And this is going to give us our moles of sodium carbonate. And that is your first mark in the bag. And you'll always be able to work out the moles of something in a titration equation. So you get 3.1 times 10 to the minus 3 sodium carbonate. Now what we do is we go up to the equation and we check the ratio. The ratio of sodium carbonate to nitric acid is 1 to 2. Look where I'm writing it there. It's 1 to 2 ratio. This means if I have 3.1 times 10 to the minus 3 of sodium carbonate, I'll have double of nitric acid. So double that up, we've got 6.2 times 10 to the minus 3 of nitric acid. Now we know our moles of nitric acid. We can work back to work out the concentration. And if you look at the triangle, we just do N over V, and that's going to give us C. And that's going to give us a beautiful 5 marks. So 6.2 times 10 to the minus 3. Remember to convert the volume of nitric acid, the 23.6, into decimeters. So divide by 1,000, you get 0.0236. Whack that into the calculator, and you'll now get the concentration of the nitric acid, but it wants it in 3 significant figures. So 0.2627. If we want to put that in 3 significant figures, it's going to be 0.263. And don't forget to write moles per decimeter. Beautiful. Okay, let's move on. Hopefully you got 5 marks. Let's go. Don't forget to pause the video and have a go with each of these. When hydrochloric acid dissolves in water, hydrogen ions and chloride ions are produced. A solution of hydrochloric acid with a pH of 4.5 has a concentration of hydrogen ions 3.16 times 10 to the minus 5 mole per decimeter. What is the concentration of hydrogen ions in a solution of hydrochloric acid with a pH of 2.5? Right, what is pH? Every movement of 1 pH is a factor of 10. So if I'm going down in pH from 5 to 4, I'm increasing my hydrogen ion concentration by times 10. So we're moving here from 4.5 to 2.5. So we're increasing the concentration by times 10 by times 10. So you just need to do 3.16 times 10 to the minus 5 times 100. And the answer is going to be 3.16 times 10 to the minus 3. Which element has atoms that have the same electronic structure as the chloride ion? So you go to the periodic table, and if you look in the periodic table, you'll see that chlorine has the structure 287. So a chloride ion has the structure 288 because it steals an electron. What element in the periodic table has the structure 288? If you look up in the periodic table, the only element with 18 electrons is argon. So argon is your answer. And there we go. Okie dokie, we're up to 6.1. This question is about the uses of metals in electrical wires. Electrical wires can be made from aluminium, copper, and silver. Figure 8, figure 6, I can't read, need my glasses, shows 3 uses of electrical wires. Wires can be used in overhead cables, they can be used in wiring in plugs and around the home, and they can be used in tiny little printed circuit boards, such as in your mobile phone or your laptop. So scrolling down, we have a little table here which shows the electrical conductivity of silver, copper, and aluminium, and the density of aluminium, copper, and silver, and the cost per kilo. Aluminium's only 150, copper's 7, and silver a whopping 640 pound a kilo. So evaluate the use of aluminium, copper, and silver for the types of electrical wires shown in figure 6. So basically for each of these in figure 6, you're going to kind of get 2 marks for the overhead cables, the wiring in the home, and the printed circuit board. So choose which metal's the best and state why for each one of these. You might also want to say why the others aren't so good. So let's get into the answers. Aluminium's got a low density. That means it's going to be the best for the overhead cables. We probably should say, however, copper and silver, their density is too high, so they'd be rubbish as overhead cables. So we could word it like that, or we could say we could go through just all with aluminium, could split it up like that and talk about aluminium for all of them. So aluminium, the low density, best for the cables, not as good as an electrical conductor as the other, so not as good in wires, I should say, or printed circuit boards, but I'm trying to bang out the answer quickly. Silver is the best conductor, So silver is the best at conducting electricity, so would be good in printed circuit boards where you only need a small amount. However, silver is very expensive, so silver is probably not good for wiring in the homes. Think of how many wires there are in somebody's house. Couldn't make all of that out of silver. It costs millions of pounds. And it's too heavy to be used in overhead cables, or too dense is the correct terminology, but you get the meaning, right? So you're really getting 2 marks for talking about aluminium, silver, or copper, or you could word this question by individually talking about overhead cables, talking about all 3 metals, then wiring in the homes, all 3 metals, and then talking about circuit boards and all 3 metals. It's your choice how you do it. So, just going through silver here and talking about all three and what it's good for and what it isn't. It's an evaluation, so you're kind of saying what something's good for and what it isn't, advantage and disadvantage. And finally, we've got copper. Copper's probably too dense to be used in overhead cables. It's a very good electrical conductor, so good in wiring, and it's cheaper than silver. So it might not be as good at conducting as silver, but it's almost as good as silver as a conductor, and it is like 9 times cheaper than silver. So, yeah, it's the choice for wiring in the homes. To be honest, you could use copper in printed circuit boards, but where you want really fast connectivity in your high-end phones, high-end electrical circuitry, you might go for silver for that extra conductivity where you don't care about price. And there you go. Copper's a good compromise between price and electrical conductivity. There you go. And we should mention that copper is probably too dense for overhead cables. Okay, let's look at the next question, 6.2. Describe how metals conduct electricity. So just think, what do you know about metallic structure? Well, they have delocalized electrons. Everybody knows that. You'll all get that mark. But they also, people forget, these delocalized electrons, nearly said something a bit dodgy there. These delocalized electrons surround positive ions in a giant metallic structure. Okay, and this sea of electrons, or delocalized electrons, can carry charge through the structure. So that's how they conduct electricity. The sea of delocalized electrons carry charge through the giant metallic structure. Okay, so I would just go for all points there. It's 3 marks. I want to get all of the marks. So I want to say they've got a giant metallic structure with positive ions surrounded by a sea of delocalized electrons. The delocalized electrons can carry the charge or the current through the structure. And that will get me my 3 marks. Whoopee doo. All right, let's move on. 6.3. Electrical wires are usually made of pure metals and not alloys. This is because your metals are better electrical conductors. Suggests why alloys do not conduct electricity as well as pure metals. So you might be going, oh my God, I've done alloys and strength, but I don't know about alloys and conductivity. What? Well, you just got to put down what you know about alloys. They're made of elements of different sizes. What does that do? It disrupts the layers. If it disrupts the layers, maybe it makes it harder for the electricity, for the current or charge to flow or be carried by the delocalized electrons. Also, if the alloys contain atoms that are not metal, like steel contains carbon, they won't have delocalized electrons. So you have less delocalized electrons. Okay, I'm waffling. Time to get on. Question 7's about electrolysis. Complete the half equation for the reaction occurring at the negative electrode. So if I've got Al3 plus, just add 3 electrons for it to become aluminium. Obviously, if you've got plus 3, you just add 3 minus, it becomes 0, which neutral atoms, all atoms are neutral, they have no charge. So if you want to make an atom from an ion, you need to add electrons. Well, yeah, all right. 7.2, cryolites. Cryolite contains sodium ions as well as aluminium 3 plus ions. Suggest one reason why sodium is not a product of electrolysis. So it's a suggest question. Just think, what do you know about sodium and aluminium? Well, sodium is more reactive. So hopefully, even if you're not sure what they're banging on about here, you go for the only thing you know the difference. Maybe it's because sodium is more reactive than aluminium. And the reason is sodium is more reactive, so it actually stays in the molten solution or the molten electrolyte and doesn't leave the electrolyte. The aluminium is less reactive and that comes out. Okay, a student investigated the electrolysis of an aqueous solution of different compounds. Figure 7 shows the apparatus. We've got 2 test tubes, an aqueous solution, 2 stoppers, and we have 2 electrodes, anode and cathode. Hydrogen ions were produced at the negative electrode and oxygen was produced at the positive electrode. Explain how oxygen was produced from water during electrolysis. So this is quite difficult, but essentially water is H2O and it's made of H plus, which is hydrogen ions, and it's made from OH minus, which is hydroxide ions. So actually, if in a glass of water, you've got loads of hydrogen ions and hydroxide ions. And what happens is the hydroxide ions are attracted to the positive electrode. So these anions or hydroxide ions are attracted to the anode. And when they go there to the positive electrode, they form oxygen. Now, because we've got hydrogen, they're going to make water as well. And they're also going to release electrons. And now you just have to balance it. I'm going to need 4 hydroxide ions so that I can put a 2 in front of the H2O over here, and that will make 4 hydrogens, and that gives us a total of 4 oxygens, and I need 4 electrons. So this equation will get you most of the marks as it shows you what's happening. But what I could do is put this in words and say, well, hydroxide ions go to the positive electrode because opposites attract. They're negative, the positive electrode is positive, so hydroxide ions go there because opposites attract. I then could also say what is happening. What's happened to the hydroxide ions? Have they gained or lost electrons? Well, if the electrons are on the right side of the equation, they've lost electrons, so they've been oxidized. So I could say hydroxide ions are attracted to the positive electrode where they are oxidized, where they lose electrons, to form oxygen gas. So we can also say that. I mean, the equation explains most of it and will pick up most of the marks for you right there. Coolio. So once again, let me read you through the nuts and bolts of this answer. Water is made up or breaks down into hydroxide and hydrogen ions. The hydroxide ions are attracted to the positive electrode, opposites attract, where they get oxidized, releasing oxygen. And that is going to get you your 4 marks. Okay, so it's going to get all your lovely 4 marks. So let's move on to 7.4. Here we go. The student compared the volumes of the 2 gases collected. How can the student change the apparatus to compare the volumes of the gases produced more accurately? Give a reason for your answer. So I'd use a gas syringe or I'd use a calibrated test tube. That means a test tube which actually has lines and a scale on it. You could say use 2 measuring cylinders, turn them upside down, fill them with water. That they're going to measure accurately the volume of gas in like centimeter cubed or milliliters that's coming off. So the reason is they have a scale, they're calibrated, so it's more easy to measure the volume. Now, 7.5, the overall equation for the reaction is 2 water molecules with a liquid symbol form 2 hydrogen gas molecules and 1 oxygen gas molecule. Water is the volume of, what is the volume, not water, what is the volume of oxygen produced when 20 centimeters of hydrogen has been produced? So if you've made 20 centimeter cubed of hydrogen, what is the volume of oxygen produced? Well, we can see here, gas volumes, by the way, are equivalent to molar volumes. So if I say I have 100 centimeters of one gas and 50 centimeters of another, the one with 100 centimeters is double the moles of the 50 centimeters. So when we're dealing with gases in chemistry at RTP, room temperature and pressure, the volume is the same as saying moles, like it's equivalent to moles relatively. Okay, so if I have a ratio of 2 to 1 with the hydrogen and I have 20 centimeters of hydrogen, the 2 to 1 is the moles. This means that for every 2 moles of hydrogen, I make 1 mole of oxygen. So how many centimeters of oxygen must I have? And the answer is 10. So ratio of 2 to 1. So if I have 20 centimeters of hydrogen, I must have 10 centimeters of oxygen. 2 to 1 ratio. Okay. And that only works with volumes of gases because they are equivalent in the amount of moles that are in each gas. 8.1, argon has the atomic number 18. Explain why argon does not form compounds. Answer in terms of electrons. We need to look at its electronic structure, so let's write that out. Its electronic structure is 2 electrons in the first shell, 8 in the next, and then 8 in the third shell. What can we say about this electronic structure? We can say it has a full outer shell, 1 mark, so will not form ions or will not react to form ions. It doesn't need to give away electrons or to gain electrons to be oxidized or reduced in order to gain a full outer shell. It doesn't need to react with other elements. It has a full outer shell. I'd probably also put here that no need for it to form an ion. It doesn't need to give away or take electrons. Okay. 8.2, phosphorus, element letter P, the symbol is the element below nitrogen in the periodic table. Predict the formula of the compound formed between phosphorus and hydrogen. Let's think, they've told us about nitrogen. What group of the periodic table is nitrogen in? Well, nitrogen is in group 5 of the periodic table. You can look it up on your data sheet. Because nitrogen is in group 5 and phosphorus is in group 5, I'd expect them to react the same. So what's the formula between nitrogen and hydrogen? Well, nitrogen forms ammonia, NH3. So I'm expecting phosphorus to form pH3 because they're in the same group. There we go. It's in group 5. It needs 3 electrons. It gets them from the 3 hydrogens to get a full outer shell of 8. Covalently bonds, they're non-metals. So it's going to share 3 with those 3 hydrogen atoms. Right, let's look at 8.3. Tellurium is an element with an atomic number of 52. Predict whether tellurium, or tellurium, however you say it, reacts with metals. Explain your answer. Answer in terms of the position of tellurium in the periodic table. Look over here. Let's have a look where tellurium is. It's in group 6. You can see there. Let me just get rid of this. Right, yeah, it's in group 6. You can see the symbol Te here. So how would I predict it will react? Well, if it's in group 6, it's a non-metal. How's it going to react with metals? What sort of bonding is it going to form if it's in group 6 and it's a non-metal? How will it react with a metal? Well, you know that non-metals and metals form ionic compounds. They gain and lose electrons with each other. So group 6 is a non-metal. It forms an ionic compound with metals. What type of ion would a group 6 element be? Think of oxygen. What type of ion is oxygen? Well, it needs 2 electrons, so it's going to take 2 electrons off the metal. It's going to become a negative ion in order to become a full outer shell. It'll be a -2 ion with a metal. So yeah, it could react with a group 2 metal where it would steal both the electrons, or it could react with 2 group 1 metals. So all different ways. All right, barium is an element in group 2 of the periodic table. Barium reacts with hydrochloric acid. Remember to pause the video, have a go. 8.4 suggests 2 observations that be made when barium reacts with hydrochloric acid. What I'm going to do here is write out the equation, because that will help me work out what I would observe. It's the state symbols that tell you what you would observe in reaction. So always pay attention to state symbols. So barium plus hydrochloric acid goes to BaCl2, which is barium chloride. Why Cl2 and not Cl? Because barium's in group 2, so it's a +2 ion. Cl's in group 7, -1 ion. And it gives off hydrogen gas. So let's write in the symbols. All acids are aqueous, so put an AQ next to any acid. Barium chloride is soluble. Chloride salts are all soluble. Hydrogen's a gas. So I'm going to see this solid silver. I'm guessing it's silver. Barium's a metal, right? It's in group 2. It's going to be kind of grey or silver. So we're going to see this grey silver solid disappear as it forms a solution and a gas. And I'm going to see bubbles of gas forming in the solution. So I'm going to see a grey solid disappear, or barium, or the solid disappear. And I'm going to see bubbles of gas formed. You can't tell they're hydrogen, but they are hydrogen, okay? So you won't get the mark if you say, I can see hydrogen form. You'd need to say bubbles of hydrogen gas, really. Write a balanced symbol equation for the reaction. Well, I just did that. So this is exactly what I've just done up there. So you just got to write this out. And they want the symbols as well, which I did up there as well. Barium's a solid. It's a metal, right? There's only one liquid metal. That's mercury. Hydrochloric acid's always aqueous. Every acid is aqueous. The salt chloride salts are soluble, so they're aqueous, and hydrogen's a gas. So it has the symbol G. All right, let's move on to question 9. This question is about displacement reactions. Iron is extracted from iron oxide by a displacement reaction with carbon. The equation for the reaction is Fe2O3 plus 3C goes to 2Fe plus 3CO. Which substance in the equation is reduced? Pause the video, have a go, people. What does reduction mean? Remember that reduction is gain of electrons, oil rig. Reduction is gain of electrons, or it is the loss of oxygen. Give one reason for your answer. Now, look what I've underlined. It says in terms of oxygen. Right, they don't want the electrons definition. So they want us to say what has lost oxygen. Well, it's the iron oxide, Fe2O3, that lost the oxygen to become Fe. All right, people, let's move on to the next question. There we go. 9.2. Which expression shows how to calculate the mass of carbon needed to produce 1 mole of iron from iron oxide? So if we want to make 1 mole of iron, how would we work out the mass of carbon? Well, we're going to need a ratio of 3 to 2 with carbon to find out the amount of moles needed. Now, if you remember the equation is mass, the moles equation, over mR times moles. I use N for moles. So mass over mR times moles, or AR, you can think of that as. So we want to do this answer here, 3 over 2 times 12. And what you're really doing there, they say times 12 grams, it's really times 12 the MR. So you're really doing the number of moles times the MR equals the mass. So this is really you doing AR for carbon is 12, and you're timesing that by the number of moles, which is 3 over 2. You might say, how do I need to know I know 3 over 2? Well, if iron is 1, you're going to need 1.5 carbon, or 3 over 2. Think if you need 3 carbons to 2 irons, then if iron is 1, as it says here, 1 mole of iron. So if Fe is 1, what would C be? It'd be 1.5, or 3 over 2. So that's the moles of carbon times its AR of 12, and that will give you the mass, which will be 1.5 times 12, so like 18 grams. Anyway, they don't have, that's all you need to do is tick that second box there. Okay, let's zing on. These were the other possible answers. This looks like a dirty question. A student investigated displacement reactions of 4 different metals represented by A, B, C, and D. So they're basically saying these aren't the real names of the metals, A, B, C, and D. They're not the chemical symbols for the metals. You won't find any chemical symbols in the periodic table. It wouldn't be like that. C for carbon, yeah. You won't find a capital A or a capital D like that. The student added each metal to aqueous solutions of metal nitrates and observed whether a reaction took place. Table 6 shows the information about the 3 reaction mixtures. So let's zoom in a little. Reaction 1, we had metal A. It reacted with B nitrate. B's a metal. And look, B got displaced. It got pushed out on its own. Let's look at reaction 2. Metal C reacted with A nitrate, and C pushed A out of its nitrate. So C did that. And then metal C reacted with D nitrate, but there was no reaction. Okay, the ionic equation for reaction 1 is A plus 2B plus goes to 2B plus A2 plus. Why is this a redox reaction? So is it A gains electrons and B loses electrons? A loses electrons and B gains electrons. Both A and B plus gain electrons. Both A and B plus lose electrons. Well, let's check it out. Redox reactions, you always get something gaining electrons and something losing, but we can see what is gaining and losing. Look at A. A goes from normal A to A2 plus. So what's happened? Well, A lost 2 electrons. and that's why it ends up being 2 plus. Now let's look at B plus. B plus goes to just B without any charge. So B plus goes to B. So it gained electrons or gained an electron. So what we can say here is A gains electrons. No, A lost electrons. So we know that this one is wrong. A loses electrons. That's true. And B plus gains electrons. Yes, we can see that's true. Let's just check the others. Both A and B plus gain electrons. No, A lost electrons. Both A and B plus lose electrons. A lost electrons, that bit's true, but B plus, did it lose electrons? No, it went from B plus to no charge, so it must have gained an electron. So the correct answer is the second one here. Let's sing down. 9.4. Got a bit of a cold today, so sounding a bit rough. Which of the four metals has the greatest tendency to form positive ions? Use table 6. Which of the four metals has the greatest tendency? So it means it wants to lose electrons the most. Which one wants to form positive ions the most? That's actually quite a hard question from table 6 to work out. If you want to lose electrons the most, you are the most reactive. So which of these, A, B, C, and D, is the most reactive metal and the most eager to form ions? Well, you can see metal A here reacting with B nitrate. B wants to form an atom, and when you're in a compound, when a metal is in a compound, it is in ion form. So who wants to form an ion more, A or B? Well, look, B ends up as an atom at the end of the reaction, and A ends up as an ion. So A wants to be an ion more than B. Now let's check the next one. We've got metal C reacting with A. Who wants to be an ion more, C or A? So C's an atom, A's in ionic form here in a compound. When they react, A ends up an atom and C an ion. So C wants to be an ion more, wants to lose electrons more. Now let's see between C and D. C so far is the most reactive, wants to be an ion the most. We just established that. When it tries to react with D, C stays as an atom and D stays as an ion because it says no reaction. So it means they stay the same as over here. And that means D is the metal that most wants to be an ion because it stays as metal nitrate, as an ion essentially. So the answer here is D. I would say that was a very hard question. Which one wanted to stay as an ion the most? So if you found that really tough, don't beat yourself up. No point. Okay, 9.5. The nitrate ion has a formula NO3 minus. Which of the four metals could be aluminium? Explain your answer. Well, what do we know about aluminium? You can think about what group of the periodic table it's in. Have you had a guess? I could show you the periodic table, but I can't be bothered. It's in group 3. What does that tell us about aluminium? It tells us that aluminium is going to form a 3 plus ion. Okay? Now, in what ratio would a 3 plus ion mix with this 1 minus nitrate ion? So hopefully you'll understand that if I have NO3 minus, I'm going to need to have 3 of these nitrates to go with 1 aluminium. So my formula is going to be something along these lines with a 3 outside the brackets, meaning I'll need 3 that because that's -1. So I need to times that by 3 to cancel out the 3 plus of the aluminium. Now, is there a metal up there in table 6 that has that formula? Let's have a look. We're getting there. Here we are, guys. So let's have a little look. C is NO3 with a 3 outside, whereas A is NO3 with a 2 outside. B is just a 1-to-1, so that's a group 1 metal. A, yeah, is a group 2 metal. So it looks like it's C. Yep, D is also a group 2 metal because it's got 2 minus nitrates. We'll take out a +2 charge. So C must be in group 3 like aluminium because it requires 3 nitrates to go with 1C. And each nitrate is worth -1. So if you have 3 of them, it must be -3. So our answer here is C. That's kind of the explanation there. So the explanation is um, aluminium has a 3 plus charge, as it is in group 3 of periodic. I'm logging this out, but you get the idea, right? It's in group 3 of the periodic table, so it has a 3 plus charge. Therefore, it will um, join with 3 nitrate ions. So the charges balance or cancel. So it will have the formula AlNO3 with a 3 outside. So you're going to get 1 mark for the metal, 1 mark for spotting that aluminium as a 3 plus charge, and nitrate ions are -1, so they need to join in that ratio. And there we go. I would say this question 9 was a very hard question. Just remember, you only need about 70% in your chemistry to get a level 9. Okay, so do not beat yourself up if you come to really difficult questions like this. Obviously, going through my walkthroughs will help you, but you're always going to get thrown in an exam something that they've never asked before or you haven't seen in a walkthrough. So you just got to be lots and lots of practice. You're ready to think on your feet. Okay, let's get into a really difficult atom economy question. This is 9.6. Metal X is extracted from an oxide of metal X by reaction with hydrogen. I've got a cold, so I might sound a bit sniffly. The equation for the reaction is XO3 plus 3H2 goes to X plus 3H2O. The percentage atom economy for obtaining metal X by this method is 77.3%. Voila. Calculate the relative atomic mass of metal X. Relative atomic mass, AR, hydrogen is 1, oxygen is 16. It's good to use a bit of a highlighter to highlight key things. First thing off the bat here is you're going to get 1 mark if you know the atom economy equation off by heart. So it's going to get us off the board. Atom economy equals kind of like the MR of, or AR, whatever, of useful products over total MR of, oh God, I can't even write properly. Total MR of products. And then we're going to times 100. Now we know that we've got the answer. It's 77.3. So we're going to start setting this out and working it out. So we know that what's the useful product? Well, it gives us in the question, calculate X. This is all about obtaining X, this equation. So we know that X is the useful product. So we're going to set out our equation like this. X over the total MR, which is going to be X plus 3H2O is equal, oops, sorry, times 100 is equal to 77.3. Now, those of you that are A star maths with kid super duper mega minds, you could probably go and solve this now. You want to solve this to find X. If that's the case, pause the video, have a go, and I'm going to go through the answers. So this is how I did it, but there are many ways to skin a cat. So first up, I am going to calculate what 3 H2Os are. Well, we've got H1, H is 1, O is 16, so H2O is equal to 3 times 18. 3 times 10 is 30, 3 8s are 24, that equals 54. So we can rewrite this with 3H2O as 54. That's a bit long, isn't it? To rewrite that all out like that? Oh, well, let's do it. So X plus 54 times 100 equals 77.3. Now, there's 2 ways to go from here. Some people say, okay, I'm going to divide both sides by 100 to get rid of the times 100. I'm not going to do that. I'm going to times both sides by X plus 54. So that's my next step, is to times both sides by X plus 54. And what that's going to do, that's going to get rid of that X plus 54 there, and I can write it all out over here. So we're now going to have X times 100 is equal to 77.3 times by, in brackets, and this is the bit where a lot of people will make a mistake, this next step, X plus 54. Okay, so Where's the mistake? A lot of people now, I'm going to times the brackets out. And a lot of people, oh, that's kind of ugly that times there because we're dealing with, I hate dealing with X and having X and writing the multiplication sign because it just looks like an X. Okay, so I've got 77.3. I should just get rid of that, shouldn't I? That's just daft of me. So let's get rid of that. Ah, we're back. Okay, let's get rid of the X. That just looks ugly. Okay, and he's still left. Never mind. That'll do. Right, so I've got X equals 100 equals 77.3 and that. Let's multiply out the brackets, geez. No, what you got to remember here, a lot of people will make a mistake, do 77.3 times X and then separately 77.3 times 54. So what we're going to have is X times 100. Why aren't I just calling it 100X? You can tell I'm not a proper mathematician. So let's just do equals 100X is equal to 77.3X plus, got to do 77.3 times 54. What the hell does that equal? 77.3. I can't do that one in my head. I know some of you countdown experts can. That equals 4174.2. So we multiplied out those brackets. Now all I need to do is take 77.3 from both sides, 77.3x, sorry, not 77.3. And that is going to leave us with, oh my gosh, a bad cough because I got a cold. 22.7x, which is equal to 4174.2. So I just need to find out how much each x is worth. So I'm going to divide 4174.2 divided by 22.7. And we're going to get an answer of 183.88. I'm going to round that to 184. Boom! Quick coughing fit, slurp a tea. That's how to solve that one. And that is a bit of a beast, I have to be honest. And even someone who is so stupid at maths as me can do it with a bit of practice. You can too. All right, like, share, subscribe. You know the coup. Let's get to the marks. Question 10. This question is about titanium oxide. 10.1. Self-cleaning windows are coated with a layer of nanoparticles of titanium dioxide. Titanium dioxide helps sunlight break down dirt particles, attracts water so dirt is washed away by rain. Nanoparticles of titanium dioxide are used instead of fine particles of titanium dioxide for coating self-cleaning windows. Suggest two reasons why. So one of them straight away, because more often than not, the answer is going to be they have a large surface area to volume ratio. That is normally going to be one of the answers right there. Whenever you're dealing with nanoparticles, it's what gives them all their lovely properties. Why is that a good thing? We might want to say less expensive as you will need less because they've got such a large surface area. They can coat it without you needing as much. Maybe also um, thinner layer means lets more light through. Obviously, if you've got a larger surface area compared to your volume, you can have a thinner layer, which is going to allow more light through. So here are two perfectly other reasonable suggestions. All right, let's zing, ding, ding. What the hell's that? Okay, I meant the down arrow. So we're now on to 10.2. So let's check it out. Titanium is extracted from titanium oxide in a two-stage process. The equation for the first stage in the process is, I've got a cold, slurp of tea. Excuse me. TiO2 plus 2Cl2 plus 2C goes to TiCl4 plus 2CO. Calculate the volume of chlorine gas needed to react completely with 100 kilograms of titanium dioxide. Relative atomic masses are 16, 48. Volume of gas per 1 mole is 24 dm. And it's a what? 6 marks. Okay, so we're going to need some equations here. But it's not too bad. Calculate the volume of chlorine gas needed to react completely with 100 kilograms of titanium dioxide. So we're starting off here with, where do you start with a big fat one like this? Well, you're going to start as soon as you see masses like 100 kg. Um, we want to start with our lovely equation you all have to know off by heart if you're hoping to get a level 7 or above, and that is mass over mR times N. N is number of moles. MR could be AR, so it depends on the question. In this case, it's MR because we're dealing with this molecule of titanium oxide, or this compound. It's actually RFM, relative formula mass, but it's the same thing. So first up, we need to add that up. What is TiO2? Because that is our MR. So I want to do kind of MR. It should be RFM, but that's a technicality. Don't worry. Times M. And I want to work out, I want to rearrange that to find the moles of titanium oxide I've got. So I'm going to do M divided by MR, and that is going to give me my number of moles. So I've got 100 kilograms. That is 100,000 grams. You actually don't need to convert it. It's all to do with ratios, but I'm going to convert it. So I'm going to find the moles. So we're going to divide that by the MR. Now the MR is going to be 48 plus 2 times 16. So 48 plus 2 times 16. Okay, which is 32. What's that? 80? Yeah. So we're going to do 100,000 divided by 80 equals, we have a whopping 1,250 moles of. Now, when you're in your exam, it's always good to label what you've worked out. So I use number of moles, N is moles, and I'm saying of titanium oxide because I might get later on in the calculation and go, oh, what was that number? And I might start thinking I've calculated chlorine or something else. So label your work. So I now know my moles of titanium oxide. What do we have to do? We have to work out the volume of gas needed to react with it. Well, guess what? We've got these things called coefficients. This is part of something called stoichiometry in chemistry, and we've got a 2 in front of the chlorine. What does that tell us? That tells me that for every 1 mole of titanium oxide, I need 2 of chlorine. So we're going to use the ratio, the stoichiometry, to go, the ratio is 1 to 2. So I'm going to need to times these moles by 2. So I will need 2,500 moles of chlorine gas. So I'm going to need 2,500 moles of Cl2 is needed. I'm still trying to work out why this is 6 marks. This does not make any sense to me why this is 6 marks. This should be 4 marks maximum. Okay, so we've worked out the moles of chlorine needed. All I need to do now is check out the volume. 24 decimeters for 1 mole. So how many moles have I got? Well, I've got 2,500. So I'm just going to do 2,500 times 48. Sorry, 24. Where did I get 48 from? I think I saw 48 next to titanium. Times 24. And this is going to be the decimeters. Now, did it want the volume in centimeter cubed or something? No, it didn't. I can't believe how much marks this is worth. Never mind. Lovely bubbly. If they want to give us those marks, then give us those marks. 60,000 decimeter cubed is what we're going to need of chlorine gas. My only way of them thinking this is that you had to rearrange. First of all, you have to know the MR times N equals M. You had to rearrange it. So you're going to get a mark for doing mass over MR equals M. So 100,000 grams, you're going to get a mark for converting the kilos. Seems generous. They're also giving you a mark for working out that titanium has an RFM of 80. So that's 3 marks. This gives you 1,250 moles, which I'm presuming they gave you a mark for just pressing equals on your calculator. Seems insane. Then you had to work out the ratio was 1 to 2, so you had to multiply it by 2. So we're now on to 5 marks, and that gave you 2,500, which you then times by 24. That is bananas. Let's move on. That is the easiest 6 marker in the history of mankind, baby.
You're still here? It's over.